All right, so let's get started. We're going to do our last of our reviews here for Chapter 8. Chapter 8 was all about ethers and epoxides, but actually the first thing we learned were reactions that take place in ethers as a solvent, these Grignard and Gilman reactions. All right, so we'll focus first on these three Grignard reactions. We talked about these quite a bit. We definitely want to be able to predict products for these particular reactions. All right, so take a second and see if you can't give me the product of these three Grignard reactions. And what's the one thing we can always do to check our work? Count carbons. so remember with these Grignard reactions, you're going to be creating a new carbon-carbon bond. Nonetheless, like I said, count carbons, you should have the same number of carbons on the left-hand side as the right-hand side, right? We're just going to combine these two molecules into one. And specifically, we're going to be connecting the carbon that's at the base of my Grignard, right, at the base of the magnesium in my Grignard, rather, to the carbonyl carbon of my aldehyde or ketone. Okay? So I can start by redrawing my 1, 2, 3 carbons from my aldehyde. And then this carbonyl oxygen is going to become what new functional group in my product? OH, right? An alcohol group. So this is what was formerly my carbonyl carbon, now should have that alcohol group on it instead of an oxygen-carbon double bond. Now I'm going to draw the bond to my new carbon. That would be this one here from my Grignard. And then I just need to make sure to include whatever's on the back end of that Grignard, right? So these 1, 2, 3 carbons. So 1, 2, 3. That would be my alcohol that I got at the end. All right, again, same logic. We're going to connect this carbon here to the carbonyl carbon of this cyclohexanone. So I'm going to redraw my cyclohexanone, 6 carbons. And then if this, I'm actually going to move it over here. This was formerly my carbonyl carbon. Now instead of having a carbon-oxygen double bond, it's going to have a carbon-oxygen single bond. And then I'm going to have to draw in my new bond. So this would be the carbon from my Grignard, and then I got to put the additional 1, 2, 3 carbons on there. All right, and I can double check. So 1, 2, 3, 4, 5, 6. I can see those in that ring. Cool. All right, and then lastly, so again, same logic. I'm going to connect this carbon here to my carbonyl carbon. Okay, I can start by redrawing those. That's a little much. 4 carbons from that ketone. And again, I'm going to convert that carbon-oxygen double bond into just an OH group. Now I'm going to connect I'm going to draw my new bond in. So then this has to be the carbon that was at the base of that magnesium, so then I can just fill in my benzene ring. All right, so the products that you get at the end are a little bit big and ugly, right? Because we've created a new carbon-carbon bond. So we get this big old ugly molecule at the end of the day. If you can make sure to keep track of who you're connecting to who, that's a really good strategy, right? So I go in and color the 2 carbons so that when I'm done, I can kind of take a step back and make sure I have the right connection. It's a really good habit to get into if you're having trouble drawing these products. All right, first identify. First thing I did was say, I'm going to connect this carbon here at the base of my magnesium with this carbonyl carbon here, and then I went from there, right? So you got to know who you're sticking together. All right, so we also learned about another type of reaction that uses ethers as solvents that create carbon-carbon bonds, and these are called Gilman reactions. The Gilman reagents are those copper lithiums. we didn't go over these quite as much as we did the Grignards, so I'm going to work through this first one, and then you guys can sort of copy that logic going forward here. Again, we're creating a new carbon-carbon bond. This time we're attaching the carbon that's at the base of my copper to the carbon that's at the base of my halide on the neighboring molecule. That's going to be my new carbon-carbon bond between those two. Remember, the Gilman reagent has this like 2 down here that you just ignore. All right, you're only sticking one of these ethyl groups on there, these 2 carbon groups on there. That's just how the reagent looks. So I'm going to start by redrawing my 1, 2, 3 carbons from my 1 substrate, and then add my new bond in. That means this one has to be that blue carbon, so I'm going to finish it off. All right, and I've connected my 1, 2, 3 orange carbons to my 1, 2 blue carbons. All right, so take a second and see if you can't finish those last 2 off. All right, so again, I'm going to identify which 2 carbons I'm connecting. The carbon that's at the base of this copper with the carbon that's at the base of this bromine. Those are the 2 that I should have. That should be my new carbon-carbon bond. All right, so I can redraw those original, 5 carbons. But then here was my orange carbon, so now I'm going to draw a new bond, meaning that this has to be that blue carbon. And then I'm going to go ahead and put in the rest of those carbons from my Gilman fragment, my little pentagon. Double check by counting carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Cool. All right, and now this is like the only kind of special consideration that we had when we had these Gilman reagents, was if you started out with an alkene, we said that it would preserve the stereochemistry, meaning if you started out with an E alkene, you should have an E alkene as a product. If you started out with a Z alkene, you should have a Z alkene as the product, right? So which one would this one be, E or Z? Do you remember that stupid thing I told you to remember that'll help it stick in your mind? Z's are Z-zame-zide, right? The 2 groups are pointed on the same side of the double bond. So is this E or Z? Who thinks it's E? Who thinks it's Z? Yeah, it's Z. okay? These two groups, this bromine and this one over here, are pointed on opposite sides. If they were pointed on the same side, it would look like this. Right? That would be the the Z version of that same molecule. So, bottom line, I mean, it's not terribly crazy. We just have to make sure to connect it the same way. So, when I'm going to connect this carbon here to this carbon here, I'm going to redraw my alkene. Again, it's going to go, new bond's going to be here. I'm just going to make sure to draw it on the same side, so pointed in opposite directions. All right, so then let's mix it up. Take a second and give me the product if instead I had started you out with this substrate here. How would that change things? So again, I'm going to start by drawing my alkenes, 4 carbons. But now when I attach that Gilman, I'm going to do so that it's pointed on the same side, because that's what it was with my starting substrates. So this is my new carbon here, or rather my new carbon bond here. So that would be my product. Okay, so that was one kind of special consideration we had to make with our Gilmans, is again, it preserves stereochemistry. Cool, all right. So now specifically for the Grignards, we did quite a lot with Grignards. We also want to be able to work backwards, right? So if I give you an alcohol, you got to tell me which 2 substrates, an alkyl halide, that's not true, sorry, an aldehyde or ketone, and the Grignard, to form such a compound. Okay, so everybody take a second and see if you can't tell me which 2 substrates, which substrate and reagent I should use to create this alcohol here. so let's do one of these and I'll give you a little bit of time to work on the other ones, but sort of go through the logic here. So the one thing that I can say for certain looking at my product is that this carbon right here, because it's the carbon at the base of that OH group, that has to be my carbonyl carbon in my aldehyde or ketone. Right? That carbon there is definitely going to have a carbon-oxygen double bond when I draw my substrate and reagent. Okay? That's also the carbon that the new carbon-carbon bond has formed between. The question is it going to be this my new carbon-carbon bond on this side here, or is this my new carbon-carbon bond? All right? And oftentimes in our reactions, we have this sort of logic of like more highly substituted, less highly substituted. There's some sort of logic as to which fragment's going to be what. Grignard reactions are just extremely flexible in that it really doesn't matter which half you want to call, which bond you want to say is your new carbon-carbon bond. Right? So there would have been two answers here that would have been perfectly fine, perfectly acceptable. One, if you had said that this was your new carbon-carbon bond, meaning that these orange carbons here would belong to the aldehyde or ketone. In this case, it would be an aldehyde. Right, so I could have this 4-carbon aldehyde, and then since that's my new carbon-carbon bond, these two would belong to my Grignard. That would have been perfectly acceptable. All right, so that would have been one set of answers that I would have accepted for full credit. The other one would be if, let's get rid of all these colorings. If I had instead said that the carbon-carbon bond on the other side, this was my new bond. That means that these 3 carbons would belong to my, in this case it'd be an aldehyde. And the remaining carbons, 1, 2, 3, would be from my Grignard. All right, so either one of those would have been acceptable answers for the formation of this particular alcohol. All right, the one thing that we know for sure is that the carbon at the base of the oxygen is your carbonyl carbon. Any of those carbon-carbon bonds with that carbon right there could be the new one that was formed in the reaction. There's no logic as to what has to be the Grignard chunk and what has to be the aldehyde or ketone chunk. All right, so take a second and see if you can't finish this off. You only have to give me one if there is multiple answers. You don't have to give me all of them. All right, but using what we just went over, see if you can't figure out the remaining 2 problems. Count your carbons also, right? Always the way that we can double check. All right, so for this one, what do I know about this carbon right here? Because it's at the base of my oxygen, what's it going to be on the other side? A carbonyl carbon, yes, awesome. All right, yeah, so that carbon right there is going to have that carbon-oxygen double bond, which means that the new bond is formed between that carbon and one of its neighbors. In this case, it's only got that one neighbor, so this has to be my new bond that was formed here. All right, that orange carbon will be on my aldehyde or ketone, and this blue carbon here will be my Grignard. So in this case, there was actually only one way to do it because there was only one possibility for our new bond that formed. So my aldehyde would be just a simple one carbon aldehyde. So what we call formaldehyde, right? Just to sort of finish out, like this would be the bond line structure here. I know it just looks like it's kind of floating around, but remember there's an implied carbon here, and since carbon likes to have how many bonds? 4, the other 2 are just hydrogens, right? So this is the simplest aldehyde that you can have, a single carbon aldehyde. This is called formaldehyde. If you ever dissected anything in biology, you no doubt got a good whiff of this stuff. It's not terribly pleasant, but nonetheless, that's going to be our aldehyde in this case. And our Grignard will then be these 1, 2, 3, 4 carbons. Right there. All right, and so for the last one, again, I know right off the bat that this carbon here at the base of that oxygen is that carbonyl carbon on my reactant side. So any of these bonds here, this one, or this one could all be the new carbon-carbon bond that was formed in this reaction. All right, you can convince yourself that these two here, if I picked one of those to be either one of those to be my new bond, I'd get the same set of reactants. All right, so really there's only going to be 2 possibilities here, so I'm just going to pick one kind of arbitrarily. Okay, so if we said that this was our new carbon, where that yellow arrow is, that means that this chunk here was what? The aldehyde or the Grignard, or the aldehyde or ketone or the Grignard? The ketone, right? Those carbons there, because it contains that carbon with that oxygen bound to it, that would have to be my ketone. What do we call this 3-carbon ketone here? Acetone, yep. And then we have these 1, 2 carbons from my Grignard. All right, the other possibility would be if I said that that other carbon was my new bond. Let me get rid of my colorings. If I said that this was my, if I said that this was my new bond here, that means that all these other carbons, 1, 2, 3, 4, would be my ketone. And my Grignard would then just be this 1-carbon Grignard over here. All right, so again, if there's more than one possibility, any one of these would be acceptable. You give full credit for either one of them. With the Grignards, we don't have any sort of logic as to what has to be the Grignard fragment and what has to be the aldehyde or ketone fragment. You just need to identify which one could possibly be your new carbon-carbon bond and split them up. All right, the other reaction we talked about working backwards for in this chapter was the synthesis of ethers, what's called a Williamson synthesis here. And so you're going to draw me the two reactants are alkoxide ion and an alkyl halide that's needed to synthesize the following ether using a Williamson ether synthesis. All right, and let's just remember real quick, what the heck do I mean by an alkoxide ion? Yeah, so it's like a deprotonated alcohol, right? So an alcohol where that H has been removed and replaced with an oxygen with a negative charge. Then of course an alkyl halide is going to be something with a halogen. All right, so let's do this first one. So again, this is the ether synthesis. So that's my product. How I'm going to get to my reactants that formed this ether. So I'm going to start with what I'm given, and I'm going to chop it at that oxygen, right? That's going to be my two fragments. So I'm going to split it apart there. And the question is going to be what goes on the carbons on either side. One of them is going to have that halide. The other one is going to have that oxygen with the negative charge, going to be my alkoxide, right? So there's my two fragments. I got to make one of them the alkoxide and one of them the halide. In this case, they're identical, right? So there's not sort of going to be any whatever. Just make one of them your alkoxide and one of them your halide, right? Because those two fragments are identical. Unlike the Grignard, though, we do have a logic as to what should go on what side. Does anybody remember what that is? For which side? No, so the halide's going to go on the less substituted carbon, the lower substitution. Okay, so we'll make a note. I guess I did it in blue, so I'll do it in blue. Halide on the less highly substituted carbon. All right, so now see if you can't use that same logic for these last two here. so I'm going to take my ether and I'm going to chop it at that oxygen into its two fragments. And I got to figure out what goes on this carbon here and what goes on this carbon here. Okay, I'm going to split these up. And again, we're going to put the halogen on the less highly substituted carbon. So is it going to go on the blue or the orange? The orange. So the orange should have my halogen. I guess I should have mixed my colors. And the blue will be my alkoxide ion. All right, same game here. I'm going to chop at that oxygen, and I got to figure out what goes on this carbon here and what goes on this carbon here. And where's the halide going to go, on the blue or the orange carbon? The orange, because that's the less substituted carbon. So that's my alkoxide ion. Cool? So those are this is this Williamson ether synthesis. If you mix an alkoxide ion and an alkyl halide together, you will get an ether. And again, to make the reaction more efficient, we're going to choose the less highly substituted side to be our halide. All right, and lastly, we learned about one reaction for ethers, but then a few reactions for epoxides as well. All right, and for the sake of time, I'm going to go through this first one pretty quickly because it's literally the exact same logic as you applied for the Williamson ether synthesis. Now you're breaking your ether apart, but it's going to break apart into an alkyl halide, and in this case, instead of being an alkoxide, it's just going to be an alcohol. All right, but again, you're going to chop at that oxygen. You're going to ask yourself what goes on either side. And again, the exact same logic as before, where we're going to put the halide on the less substituted carbon. So this would be, in this case, it's a chlorine. And now instead of an alkoxide, it's an OH. All right, but the exact same logic as our Williamson ether synthesis. This is the reverse reaction there. All right, before we were creating an ether with our two substrates, now an ether is falling apart in the presence of this acid. All right, so let's go through one of these epoxide reactions here, and then I'll let you guys do the other ones. Make a little bit of room so we can make a note. Remember, these reactions of epoxides we called ring opening reactions. Epoxides are ethers, but they're a very specific type of ether, where that oxygen has been squeezed into this three-membered ring, this triangle here. These triangles are not very happy. They're not very stable because the bond angles are much smaller than carbon would like to have, right? So this ring really wants to pop open, and that's exactly what we're going to see with these reactions. All right, these are going to be ring opening reactions. And what we're going to see is that our nucleophile, so over here, what did I tell you do when you see sodium? Erase it and replace it with a negative charge. Alright, so that's going to be my nucleophile. I'm going to attach my oxygen to one of the carbons on my epoxide. And importantly, that will break this carbon-oxygen bond in the process, all right? That's what these reactions are all about. This nucleophile forming a new bond with this carbon here and breaking this ring open. All right, importantly though, that oxygen we're going to see stays bound to that neighboring carbon there. So in this case, my product would be my 2 carbons from my epoxide. I have my nucleophile attached on one side, so this would be this. But now my adjacent carbon, the other one from my epoxide, still has that oxygen bound. All right, so these reactions will look like this, where you have a nucleophile being added to one side of your epoxide, and that means an alcohol group is forming on the neighboring carbon. So this is the pattern we're going to see over and over again for these reactions. Be able to concatenate them. All right, my bad. So finish these off here. So again, I see this sodium. I'm going to get rid of it and replace it with a negative charge. So I'm going to be connecting this oxygen to the carbon in my epoxide. However, I have these, this is now not a symmetric epoxide, so I would get a different carbon depending, a different product depending on whether my new bond was with the blue carbon or the orange carbon. Which one is going to have that new carbon-oxygen bond, blue or orange? Why blue? What is it? Less substituted, right? So the thing, and really the logic is that it's less crowded, right? So in terms of the nucleophile being able to reach over and form a new bond with that carbon, it's going to go on the less highly substituted carbon because it's just simply more accessible. Okay, so that's my new bond that's going to form. And again, that'll break that bond there. So my product will have that oxygen still on that orange carbon and my nucleophile attached to that blue carbon. All right, so again, what we're going to see, if you look at our generic scheme up above here, what we're going to see is our nucleophile is added to one carbon in that epoxide ring, and the neighboring carbon retains that OH group. All right, so these were the alkoxide ion, the hydroxide ion. That would be sort of like under basic conditions. Those are both good bases and good nucleophiles. You could do the same thing under acidic conditions. If you use an acid like hydrochloric acid, then your nucleophile would be the chloride ion. All right, but again, we have this same logic where we can attach it here or here. And again, we're going to pick the less substituted carbon. All right, so these are these ring opening reactions of epoxides. And again, the signature here is the nucleophile is being added to one carbon from the ring, and the neighboring carbon retains that epoxide oxygen. It becomes an OH group. So you have these two functional groups that are formed that are 2 carbons apart. Cool. Almost there. All right, so what do we have on Monday? Exam. All right. And I will race like the wind to get them back to you on Wednesday, so you'll have them to study for the final. Which sounds miserable.